Hello, welcome to my presentation for my assessment in quantum field theory. So I'm Abby, and this is my answer to the question we were given on decay rate. So we'll start by kind of presenting the question itself. So a system of three real scalar fields, phi 1, 2 and 3, is described by the Lagrangian as follows in equation 1 here. So part I was to present the Feynman rules for this theory. So in momentum space, the Feynman rules are as follows: minus I lambda for a vertex, I over p squared minus m squared plus I epsilon for a propagator with momentum p flowing along it, 1 over 2 pi to the power 4 integral d4k for each independent loop, 2 pi to the power 4 delta function of the initial momentum minus the final momentum equals the overall momentum conservation. A combinatorial symmetry factor 1 over modulus g, where modulus g is the order of the symmetry group of the diagram keeping external lines fixed. These rules are used for reconstructing from Feynman diagrams using dummy variables at the vertices. In this case, we've used momentum space as it's more commonly used in physics, particularly in particle physics, hence why we've used it for this theory in particular for our particle decays. Part 2 is to explain what the actual decay rate is. So the decay rate is the rate or the probability per unit time of usually an unstable particle decaying into one or more new particles. The differential decay rate can be defined as d tfi equals d omega fi over t. So we define this differential decay rate because it makes it easier to actually calculate the decay rate itself, which we denote as gamma a bit later on. So it's useful here to define the differential n-body phase space 2, which would be d phi n in this case in equation 2. And this allows us to write down the differential decay width as d gamma, where gamma is the decay width itself. We can then take the integral of this equation, so equation 3 here, to find the decay width or decay rate on its own, gamma, which is our final answer for the calculation of decay rate, which we'll now be doing in part 3 to see how this all works. So we will be looking for just gamma on its own. So part 3 is to calculate the decay rate gamma for the decay phi 1 goes to phi 2, phi 3. So to begin, we can start by visualising this problem a little bit using a Feynman diagram for this decay. So we do start with phi 1, so our initial particle with an initial momentum of 0 or p0, and it does have an initial mass of m. This particle then goes on to decay into two particles. So we've got phi 2 with a momentum of p2 and a mass of 0, so this particle here is massless. But then we have another particle here, phi 3, which isn't massless, but it does have a smaller mass than the initial mass given here, which is m, and has a momentum of p1. As you can see here, we have followed the Feynman rules, and we have assigned a minus I lambda at the vertex in this Feynman diagram. Now moving on to the more kind of mathematical side of this calculation, we can start by expressing the momentum. So we do start with a momentum of 0, as mentioned briefly just then on the Feynman diagram. So using this fact, we can express our individual momenta as follows. So here we use the conservation of momentum, and we start with our initial momentum of 0 and our final momentum of p2 plus p1. Simplify that further, and we then can see that p1 is equivalent to minus p2 and vice versa, so p2 is equivalent to minus p1. So we will be using this later on to kind of simplify our integrals down. We also know that the matrix element mfi is equal to minus I mu, but we need to calculate gamma, or the integral of the differential decay width. For the decay, phi 1 goes to phi 2, phi 3. So to do this, we first must calculate the matrix element modulus squared, and to do this, we go to the rest frame of phi 1, where the energy is equal to just m, and we find that the modulus of the matrix element fi squared is equal to mu squared, so that is where minus I mu times minus I mu is equal to mu squared. We also know that the differential decay rate d gamma is mu squared over 2m d phi 2, where d phi 2 is the two-body phase space because we have a decay into two particles. We can then express this d phi 2 a little bit more explicitly as follows in equation 8 with some delta functions in there, and then kind of putting this in, we can then take the integral of equation 7, substitute in the d phi 2, which then gives a decay width gamma of double integral mu squared over 2m 2 pi squared delta function m minus ep1 minus ep2 delta 3 p1 plus p2 d3 p1 d3 p2 to 2p1 to ep2. So this will be the variable that we are actually looking for. So in our final answer, it will be gamma equals. So we want to calculate these integrals in particular. So to begin kind of simplifying it down so we can actually do these integrals, we start by using our momentum expression. So we know that P1 is equal to minus P2 and vice versa. And we also know from quantum physics that E squared equals P squared plus M squared. So by doing this, we can actually find expressions for the energies, so EP1 and EP2. So we can start using the energy squared. So we'll start with EP1 squared, and we know using that expression just above that P1 squared plus EP1 squared equals P1 squared plus M squared. Square root this and we just get EP1 on its own, so we get square root P1 squared plus M2. Similarly, we can do this for EP2, so we'll start with EP2 squared equals P2 squared, and we would usually have a mass term squared there, but obviously we know that phi2 is massless, so we would just have the momentum on its own, so EP2 squared is equal to P2 squared, meaning that taking the square root, we just get the energy of P2 is equal to P2. So there's no mass addition there. We can now substitute these expressions into 9, where 9 was our gamma, or decay width, and we then get this equation here, so a little bit simplified, and we've changed all of the p's into the same p, so using that expression where p1 is equal to negative p2, and we've changed them all into the same one to make it a little bit easier for us, and we've also substituted in the expressions for the energies. To make future calculations even easier, we can convert this into spherical coordinates, where we use these following equivalences in 13, 14 and 15, which reads d3p1 equals p squared plus dp d omega equals d cos theta d phi, and an integral of d omega is 4. So substituting all of this in, we then get the following equation for gamma. So we've got another double integral, mu squared over 2m 2 pi squared delta function m minus square root p1 2 squared plus m squared minus p1. Then we've got p squared dp d omega over 4p1 square root p1 squared plus m squared. So it is starting to look a little bit complex, but there are ways that we can simplify this. So we need to evaluate this delta function in order to do this integral properly. So this delta function here with the m and the p1 and the little m there. So we need to evaluate that in order to kind of move forward with this integral. So we can do this using the equation as follows, which is kind of an expression for a delta function with a function inside it, where we can set this function p0 equals to 0. So we will be using this equation 17 here. So we will proceed by setting everything that's in our delta function equal to 0 in order to find expressions for p0 and f dash p0. So the function in the delta function, if you like, is m minus square root p0 squared plus m squared minus p0. So we've changed all the p's into p0. And then obviously we can rearrange this, and because we know that we're setting this equal to 0, so we'll rearrange it for p0, and we do end up with equation 19. So we've got big M squared minus little m squared over 2 big M. We can then use this even further, so we can go back to our f dash p0 expression. So we will differentiate equation 18 to find f dash p0, substitute in the p0 here, so where we've got obviously minus 2p0 for example, we will then put in this equation 19 that we got for p0 to make this equation here 21, which does look quite complex and quite difficult, but we will find out later how we can kind of simplify that a little bit more and make these integrals actually work. So now we can evaluate our delta function properly using equation 17, which was this one here, so this kind of standard equation for a delta function, which is written here. So this is our delta function from our actual integral, and then we've put it equivalent to the standard definition of a delta function. And then we can substitute in 19 and 21. So this was 21, the horrible looking one, and then 19 was just the equation for p0. So then we get this as our delta function here. So at first glance this does look really horrible, and it looks like it's going to be really difficult to kind of integrate that. However, we can simplify it down to something much more workable, so we can actually do this integral. Excuse me. So we start from 23, which is this big horrible one, and we can look at the multiplicative terms, so these two here, so these ones with the m's in basically, write them out here in 24, and what we can do is we can actually take out a factor of 1 over 2m to the minus 1 out of this square root here, which would leave us with this expression. So obviously after we've multiplied it out, we get something that looks a little bit like this. Do some algebraic manipulation, some simplifying, some rearranging the equations, and we do end up with this. So we end up with minus 2m squared over m squared plus little m squared. We know that this term must be positive in order for our theory to hold, in order to actually carry on with this calculation and have it be valid. So we can take the modulus of this, which gives us 2 big M squared over big M squared plus little m squared. We can then substitute this back into our equation 22, which was our expression for the delta function itself, and we then get this as our simplified delta function that we can actually work with in our equation. So we can now substitute back this expression for the delta function, or equation 29, into our original integral for gamma, which is what we're looking for our final answer, as follows here. So we've put that into our delta function there and there, and then this is kind of our integral as it stands now. So we've got double integral mu squared over big M d omega 2 pi squared 1 over 16 delta function there, and then we've got p squared dp over square root p1 squared plus m squared p1, and then we've got m squared plus m squared over m squared. Now we can finally perform our omega and p integrations as follows. We can get rid of these integral signs. The p integrations quite nicely simplifies all of these momenta terms here, and the omega integration also simplifies these pi terms here for us, so we can kind of get rid of these pi's, which is quite nice. So the omega essentially inserts a 4 pi for us to work with. And then we end up with this equation, so a little bit more simplified, got a lot of m's in there, and then we could just work with that and carry on simplifying it, so we end up with this kind of quite long multiplied out term, and then we could start factorising it again as follows. So we factorise it into brackets with the minus and pluses in there, put these m's together so they're nicely grouped into an m cubed, got these brackets, obviously this one here in the numerator and the denominator cancel, so we do end up for our final answer of gamma equals mu squared over 16 pi m cubed multiplied by m squared minus little m squared. So that is our final answer for gamma in equation 36 there, and this answer gives us the probability per unit time of the particle decaying into 2 particles, one of these of mass m, which is smaller than the initial mass of big M, and the other massless, or hence the decay rate. So this gamma is the decay rate of phi 1 decaying into phi 2 and phi 3, where phi 2 is massless and phi 3 has a mass of little m, which is smaller than initial m. So part 4 is a little bit of a reflective kind of question. So part 4, explain what happens to gamma when m tends towards big M. So if m starts to get larger or kind of towards big M, we do end up seeing that this reduction here, the little m, does get larger, which kind of impacts the decay rate and makes it smaller. So if this m, we set this equal to big M, this whole bracket here was equal to 0, which would set the whole decay rate equal to 0, which we can see here in this equation 37. If m is just tending towards big M, so it's kind of increasing, the decay rate as a whole would decrease. Similarly, we can see what happens in the opposite direction, so where little m tends towards 0 or kind of becomes infinitesimally small. There would be an increase in the overall decay rate, so the opposite of 37, because little m here, as you can see, is an actual kind of reduction factor into the decay rate. So if this is obviously getting smaller and it eventually is equal to 0, then this is the maximal decay rate, so there will be no reduction whatsoever, and when there is a reduction, it will only be quite minimal. So the decay rate actually increases when m decreases. So if m does eventually get to 0, then the decay rate is at its maximum probability of mu squared over 16 pi m cubed m squared, as this condition as a whole would eventually get rid of the deduction in this calculation here, as we can see in 38. So there's another little bit here. So could you have expected this behaviour without doing the calculation? So yes, we could. So although doing the calculation can be really informative about the actual decay width, and you can then evaluate limits, etc. by using it, we can find kind of the maximal probability, and you can obviously, it'll be different for each individual decay. You can see all the differences there as well. You can predict this behaviour still just from the knowledge of particle decay, masses and quantum field theory. So a really trivial example would be for the initial decaying particle had a mass of big M, and the final particle also had this same mass. You can see just from the Feynman diagram that this particle will not have actually decayed into a new particle, so the decay rate will be equal to 0. You can actually see things like that just from the Feynman diagram, and from how you can see the particles kind of acting after they've decayed. You can predict kind of behaviour like on this slide here, just from Feynman diagrams and your knowledge of particle decays. So that is the end of my presentation, so thank you for listening. If you've got any questions, please get in touch with me at my email, sjmccar@liverpool.ac.uk. Thank you.